So let me come to this: do copies of us exist? So this is really a question about the multiverse. And I would say that's an example of a question which is ascientific, to use the word from my friend Palmer, which he brought this up in an interview that I did with him, and I just took it and ran away with it. Okay, so again, I think I first have to explain why would someone even come up with this idea that copies of us exist. That sounds certainly a little bit weird, but that's because infinity is weird. So in this standard model of the universe that we currently use for cosmology, the universe is infinitely large. This, by the way, is also the case at the Big Bang. I know that a lot of people have this idea at the Big Bang the universe was kind of like a small ball, but that's not quite right. So in the standard cosmology, the universe is always infinitely large. What happens at the Big Bang is really that the energy density becomes infinitely large. So, but the thing with infinity is that if you have some kind of density fluctuations in this early universe, and you just go out all the way to infinity, then any kind of fluctuation will happen somewhere with probability 1. That's what infinity does to you. Now, our solar system, our galaxy, and you and I, everything we know, grew out of this early hot plasma in the universe with those small density fluctuations in them. So if you have an infinitely large universe, then those density fluctuations, they will repeat with arbitrarily small changes to them. So there would be a version of Earth that's exactly the same as ours in every detail, except that there was maybe one cosmic ray that didn't come down exactly the same way, and it didn't damage someone's DNA, and your neighbor is still alive, or something like this. So all those variations should actually exist in an infinitely large universe. But the problem is the speed of light is finite, and we cannot communicate with anything that's outside what's called our cosmological horizon. That's basically anything we can reach by sending signals with the speed of light or below. The problem being that since the expansion of the universe actually speeds up, it becomes more and more difficult to reach other galaxies. So they're receding faster from us than we can possibly communicate with them. To make a long story short, the universe may be infinite, and it may have all those copies of us, but we'll never be able to find out because we can never interact with them. So there are no observations that can refute or confirm that these copies exist. This is one of the simplest version of what's sometimes called a multiverse. One can quibble of whether those are actually other multiverses. Another example is what's called eternal inflation. So inflation is one of those theories for the early universe that I was talking about. The idea is that there is a new field which fills the universe. This field is called the inflaton field. So, and this is the only thing that exists in the early universe, and there are quantum fluctuations in that field. And from those quantum fluctuations, there are bubbles created, and those bubbles expand and give rise to the universe around us. Now, the thing is that in this infinitely large space, there are lots of those fluctuations again, and those bubbles keep on popping out forever. So there's an infinite number of big bangs going on in this eternal inflation scenario, and they'll keep on going on into all eternity. There are several variations of this idea of eternal inflation. For example, in some of those little bubbles that pop out and grow into universes, the constants of nature could be a little bit different from the one that we have here. They could also be the same. If they are different, this is often called the landscape. You may have heard of this as the string theory landscape. So this is actually where the idea comes from. String theory seems to tell you that the constants of nature should come with all possible values, so you can combine this with this idea of eternal inflation, basically by distributing the different values of the constants over the different big bangs. This is called the multiverse, though again one can debate whether this is a particularly good term. Of course, if you take the word universe to mean all that exists, then by definition the multiverse doesn't exist, which is probably not what the people who used the term intended. But that's the way that it goes with nomenclature. It doesn't really always make sense. So also in this version of the multiverse, there should be copies of us in all those other big bangs. Again, the problem is, though, there are no observations that can refute or confirm that these copies exist, because we can't interact with them. Again, you'd have to be able to send signals faster than the speed of light, or to transport yourself faster than the speed of light to get into one of those other universes. There's a final version of this copy argument that I want to mention, which you may have heard of. That's the many words interpretation of quantum mechanics. So, as I said earlier, in quantum mechanics we have two different ingredients to the time evolution. We have the Schrödinger evolution, and then we have the measurement update. The measurement update is indeterministic in the standard interpretation of quantum mechanics. Now, in the many worlds interpretation, people say, well, actually, making a measurement does not collapse the wave function. Instead, what happens is that the universe splits each time you make a measurement. So if you measure the particle, say, let's take a simple example where a particle goes on a screen and you want to know, does it go left or does it go right? In a standard interpretation, you would say, well, I've measured it and now it's on the left side, and that's the end of the story. In the many worlds interpretation, you would say, well, now I have two universes. One in which the particle went to the left side and the detector says it's on the left side, and one in which it went to the right side and the detector says it's on the right side. So now you have two universes. And this happens all the time everywhere. Like every time some kind of photon bumps into the wall, the universe splits. So there are lots of those universes. And there are copies of us in them. Because all those quantum events happen around us. They even happen in your brain. You know, they happen every time you turn on a lamp. It's not a rare event. So in the many worlds interpretation, copies of us are all over the place, and our lives pan out in all possible ways that they can pan out. And there are a lot of people in physics who actually really believe that this is what's going on. Again, the problem is, though, there are no observations that can refute or confirm that these copies exist, because it's one thing to say, okay, the universe splits and all possible outcomes of a measurement actually do happen in some universe. In our universe, we only see one outcome. And that's what we know. And so there's no way to ever figure out if those other outcomes are actually real, or what it doesn't even really make sense to speak of something being real if you can't observe it. The reason physicists, at least some of them, believe that these copies actually do exist is the same in all cases. They basically believe that because there are equations for it, it also has to be real. So they have a set of equations. They have some reason to believe that those equations are correct because they describe something that we observe. But then they jump one step further and say, therefore, I believe that everything which is in those equations is also real, even if I can't observe it. Now the problem is, that's not a notion of real anyone ever uses. It doesn't really mean anything to say something is real if you can't interact with it, if you can't observe it. You can just assume that those mathematical structures are real, but this is an unnecessary hypothesis. You don't need it to describe anything we observe, because it pertains to those parts of the theory that we do not observe. And as I said earlier, we shouldn't use unnecessary hypotheses in our theories. That's just not allowed in science. So I think these multiverse arguments are not proper science. We can't tell if those copies are real, so we shouldn't assume that they are. But this doesn't mean that those copies are not real, because science also can tell you that they do not exist. Science doesn't really say anything about it. So if you want to believe that there are copies of you out there somewhere in the multiverse, you can believe in this. There's nothing in science that speaks against it.